you can derive a resistance value from known operating parameters. To do so, you will need to measure the voltage across the FSE system and measure the current through the FSE system. The resistance can then be determined by dividing the voltage by the current using the formula resistance equals voltage divided by current. You can also derive an ohms per meter value from the original design length. Start with the original resistance calculated from the measured resistance and original design length. Then use the original length, which is the original design length of the piping system. To find the ohms per meter value, divide the original resistance by the original length, using the formula ohms per meter equals resistance divided by length. You can then apply this ohms per meter value to the new length. First, determine the new length, which is the new design length of the piping system. Then, calculate the new resistance, which is the estimated new resistance based on the ohms per meter value and new length. To do this, multiply the ohms per meter by the new length, using the formula new resistance equals ohms per meter multiplied by length. Please note that this calculation assumes the FSE system is uniform and has a constant resistance per unit length. It is highly recommended to verify the new resistance value by measuring the actual resistance of the modified system after installation. Always consult with the manufacturer's guidelines for specific requirements and calibration procedures. In summary, firstly, measure the voltage across the FSE system and the current flowing through it. Secondly, calculate the original resistance using the formula resistance equals voltage divided by current. Thirdly, determine the original length of the piping system. Fourthly, calculate the ohms per meter value by dividing the original resistance by the original length. Fifthly, identify the new length of the modified piping system. Sixthly, estimate the new resistance by multiplying the ohms per meter value by the new length. Seventhly, and importantly, verify the calculated resistance by physically measuring the resistance of the heat tracing system after the modifications are complete. Eighthly, refer to the manufacturer's documentation for specific guidelines and calibration procedures relevant to the particular heat tracing system. This ensures accurate and safe operation of the heat tracing. When dealing with electrical systems, safety is paramount. Always to energize the system before making any physical modifications or measurements. Employ appropriate personal protective equipment, including gloves and eye protection, to mitigate potential hazards. Consult with qualified electrical professionals to ensure compliance with relevant codes and regulations. The process of calculating heat trace resistance is valuable for maintaining the integrity and efficiency of the system. It is essential for confirming that the heat tracing is operating within its designed parameters and providing the necessary heat output. Deviations from the expected resistance values could indicate issues such as insulation degradation, damage to the heat tracing cable, or improper installation. By performing these calculations and measurements, potential problems can be identified and addressed promptly, preventing costly repairs or downtime. It is also beneficial to keep records of the resistance measurements over time to track the performance of the heat tracing system and detect any trends that may indicate deterioration or the need for maintenance. Regular inspections and testing can help to extend the lifespan of the heat tracing system and optimize its energy efficiency. Consider the impact of temperature variations on the resistance of the heat tracing material. Resistance typically increases with temperature, so it's important to account for these variations when making measurements and calculations. Manufacturers often provide temperature coefficient data that can be used to correct resistance readings for temperature changes. Also examine the connections and terminations of the heat tracing system. Loose or corroded connections can introduce additional resistance into the circuit, affecting the overall performance and potentially causing overheating. Ensure that all connections are properly tightened and protected from moisture and corrosion. Proper insulation is also crucial for the effective operation of heat tracing systems. Damaged or inadequate insulation can lead to heat loss and increased energy consumption. Inspect the insulation regularly and repair or replace it as needed to maintain optimal thermal efficiency. In addition to resistance measurements, it can be helpful to monitor the current draw of the heat tracing system. Significant deviations from the expected current draw could indicate problems such as short circuits or open circuits. Use an ammeter to measure the current and compare it to the manufacturer's specifications. Consider the length and layout of the heat tracing system when interpreting resistance measurements. Longer systems will naturally have higher overall resistance than shorter systems. Also, complex layouts with multiple branches or loops can affect the distribution of current and heat. It is important to understand the specific characteristics of the heat tracing system to accurately diagnose any issues. For complex heat tracing systems, consider using specialized testing equipment such as time domain reflectometers or thermal imaging cameras. These tools can provide valuable insights into the condition and performance of the system, helping to identify hidden problems that may not be apparent with simple resistance measurements. Regularly review and update the heat tracing system documentation, including wiring diagrams, installation instructions, and maintenance procedures. This ensures that all relevant information is readily available to personnel responsible for maintaining and troubleshooting the system. When making any modifications or repairs to the heat tracing system, always follow the manufacturer's recommendations and use approved components and materials. This helps to ensure the safety and reliability of the system. Consider the environmental conditions in which the heat tracing system operates. Exposure to harsh chemicals, extreme temperatures, or excessive moisture can accelerate the degradation of the system components. Take appropriate measures to protect the system from these environmental factors. In summary, firstly, measure the voltage and current of the heat tracing system. Secondly, calculate the original resistance using Ohm's law. Thirdly, determine the original length of the heat tracing. Fourthly, calculate the resistance per unit length. Fifthly, determine the new length of the heat tracing. Sixthly, calculate the new estimated resistance. Seventhly, verify the calculated resistance with a multimeter. Eighthly, consult the manufacturer's documentation for further information. Lastly, ensure proper safety precautions.